Hello, and welcome to our talk on this late evening. I hope you still have a bit of energy. I'm Łukasz Biały. I'm a Scala developer advocate at VirtusLab. And today with me is Michał Pałka, who is our API wizard, basically, but also senior Scala compiler engineer, part of the Scala compiler team at VirtusLab. Today, we would like to share with you our vision on where we have to move with Scala to catch the market where it will be in the future before it actually happens. It's the vision of scaling Scala well beyond its original domain. The agenda for this talk is as follows. First, we'll talk about the challenges in the domain of cloud systems development and the trends that we can already see there. Then we'll talk about the solution that we propose to the problems, and we'll explain how it works. And finally, we'll talk about our plans on how we are going to develop that, where we want to take that, and how you can help us guide this effort so that it's maximally useful to you. The reality is that we are currently building more and more software at higher and higher velocity, and we can't afford manual operations. We couldn't afford manual operations for some time now, actually. The automation in the space has been progressing. The arrival of generative AI is only going to increase the pace. It's only going to increase the strain on the operations, and it will demand even higher correctness and fewer faults in this process. So, given that DevOps is already moving towards infrastructure that is programmable, that can be managed using programs that can be used on demand, it's really sad that we are repeating the same old mistakes. In this space, however, mistakes are often much costlier than simple mistakes in application code. For example, an error in DevOps domain can misconfigure networking and render a whole bunch of workloads unavailable, which is completely different from just 500 happening on an endpoint. We can see that this process was being done the old bashy way with, for example, Helm, that is actually a data processing pipeline, if you think about it, that takes values from YAML files and then puts them into YAML files, which are then used by something like Argo CD to just apply them to Kubernetes environment. AWS used CloudFormation initially, but that turned out not to scale. So now they allow us to use actual programming languages with CDK. The same thing happened with Terraform, which also has its own HCL language, but it also evolved to have a cloud development kit that allows one to use actual programming languages. So the leader in the space is Pulumi. We have talked about this before, so I hope you are already familiar with the topic. Pulumi is an infra as code tool that allows you to use many programming languages, 3 of which are supported either partially or completely thanks to contributions from VirtusLab. With Pulumi, you use programming languages for everything related to management of infrastructure. Moreover, Pulumi allows one to embed itself, Pulumi programs, into other programs and to use infrastructure management programmatically without virtually any effort spent on integration. Finally, you can use Pulumi with our project Bisum, which is the SDK for Scala for Pulumi, so you can benefit from having your skills as Scala programmers and the safety Scala as a language brings. There is, however, a problem with all these tools, even with Pulumi with Bisum. There's still something that is missing. Let's take a look on this example chart of a cloud system deployed using Terraform. We have our services, which are potentially implemented in Scala. These applications have some requirements and interfaces that they expose and consume. These things are left, however, in a kind of an unchecked void, kind of like JavaScript programmers with Notepad++, because, for example, engineers know that order service has a RESTful API, that it uses RDS and SQS, and it has to call a payment service. But, well, to verify that things will actually align with each other, what we do, we have to do some time-consuming work with like deployments to staging environments, which are costly, with smoke tests that will happen over that. And even if we do all of that, it's still best effort integration. There are tools like protobufs that help us to bridge that gap. But even with them, the responsibility of verification, whether the applications are mutually compatible, is still left to be done manually by engineers. That is caused by the fact that infra as code layer is completely ignorant of what the applications require to run, like configuration parameters or external services that have to be available for the application to even start, and what interfaces the app exposes, and how, therefore, applications communicate with each other. All of these things are left to programmers and DevOps specialists to remember about, figure out, glue together. So the idea that we want to share with you today boils down to the central question. We know that types help to scale software engineering efforts, so why don't we use types in this space? Why are we okay with the fact that the helpful hand of compilers and type checkers extends to the border of our applications and no further? At Virtuous Lab, we want to address this problem, and since we're huge fans of Scala language, we naturally started working on it using Scala. My colleague Michał will guide you through the how we plan to improve this space.
Okay, thank you, Łukasz. The tool we're working on is codenamed Jaga. In case you're not familiar with Slavic folklore, Jaga is the name of an old and ugly witch, but as a witch, she knows how to fly a besom and do magic, and that's basically what we need. Jaga is the glue that connects applications and Pulumi managed infrastructure, allows the shapes of our applications to surface on the infra level, and allow us to verify that both applications and infrastructure are aligned with each other. It allows us to use type checking across the boundaries of apps and besom code that manages their deployment. There are a few things that Jaga does for us. First, it lets users focus on writing business logic and handles the technical details of how an application will be deployed, reducing boilerplate. Jaga allows specifying infrastructural requirements of an application directly in Scala code together with the business logic, abstracting from how the infrastructural part will be provided. Jaga verifies at compile time that applications can communicate with each other using the same data schema or protocol. Finally, Jaga reduces boilerplate by allowing one application to refer to parts of the data model of another application without the necessity of extracting them to a separate shared module. You might wonder how this is achieved, so I'll try to give you a quick overview of how Jaga works under the hood. Let's assume we have some Scala code with the business logic of our application. After it gets compiled, Jaga can inspect the tasty files inside the result jar to figure out what the application needs to get deployed properly. Then it generates helper code to be used in the definition of the infrastructure in a besom program. Jaga also instructs the build tool how to package the application so that it can be safely deployed to the cloud. If any of the infrastructural requirements of the application were not satisfied, the besom program wouldn't compile, which would prevent invalid infrastructure from being deployed. In a similar manner, Jaga can validate interactions between different applications which are supposed to be run together as a part of the same deployment. In this case, Jaga extracts the model of one application, for example, the structures of its inputs and outputs, and generates code of analogous classes that can be used by the other application. This guarantees uniform serialization and deserialization of data, but doesn't impose dependencies between class paths. At the same time, this helps avoid the jar hell problem. And finally, it also gives each application freedom of choice with regard to the backend used. For example, it could be Scala on JVM or Scala.js, Scala native or GraalVM. Yaga as a library is designed in a modular way with focus on extensibility. Yaga's core contains shared logic reusable by connectors for different technologies to make integrations between them smooth. And typically, each extension provides some SDK to ensure some uniform format of applications and allow extraction of metadata needed by the code generation. Triggering code gen and preparation of deployable artifacts are orchestrated by a dedicated SBT plugin. Currently, we only support AWS Lambdas as an extension for Yaga, but work on other connectors is in progress. To illustrate better how Yaga works, let's have a look at an example. We would like to have thumbnails in different sizes generated for images appearing in a S3 bucket using AWS Lambdas. So how can Yaga help us with that use case? The design of our system could look like this. The flow here starts when a new image gets added to an S3 bucket. Then the file edit handler, Lambda, gets a notification from the bucket and triggers the image processor, Lambda, in parallel with different parameters for the target size of a thumbnail. And for each request, the image processor loads the given image from S3, processes it, and writes back to the bucket at a different object key containing the sizes. Here's our build definition. As mentioned before, Yaga integrates with SBT via plugins, but it also offers a DSL to let users clearly express the relations between different parts of our application. For example, we can say that a module is supposed to be treated as an AWS Lambda with JVM backend. Then another module can depend on its data model, which will be shared via code generation without adding a dependency on the class path. And we can also tell Yaga to generate infrastructural helper code so that we can easily deploy a given module. Now let's see what our image processor Lambda would look like. Without going into much detail, let's just focus on the crucial sections of this code. So to tell Yaga that we're defining an AWS Lambda, we need to define a class extending a special marker class coming from Yaga's SDK for AWS. The marker class takes type parameters, which specify its shape. In case of an AWS Lambda, the shape consists of the types of Lambda's initial configuration, input data coming from handled events, and the response data, which is the result of the Lambda invocation. Custom types referenced directly or transitively by the shape by the shape types define the data model of our application. And finally, the business logic is specified by implementing just a single method with well-typed input and output. Now here's a snippet from the file edit handler Lambda implementation. As you can see, it uses some more classes coming from Yaga's SDK for AWS. The SDK provides reusable logic and gives users a possibility to abstract from the actual Lambda runtime, which could be JVM, Node.js, GraalVM, or even something else. But most importantly, it lets us reference other applications running in the same infrastructure in a type-safe way. Yaga compares type structurally to assure lambdas can talk to each other, given that they use the same schema, and it complains about mismatches during compilation. For convenience, we can refer to data classes defined in another module we depend on, thanks to the built-in data model sharing via code generation. With our business logic implemented, we can get to how our infrastructure will be defined. This is just a snippet from our entire infra definition in BSOM, but it shows how Yaga smoothly plugs into a BSOM program. Based on the Lambda handler class we defined earlier, which is file edit handler Lambda, Yaga generates a helper method for creating the Lambda resource. Thanks to the integration with the build tool, we don't have to worry about how the Lambda should be packaged so that it can be deployed. And what's important here is also that our definition of the infrastructure won't compile if the Lambda resource is not provided with a reference to another resource it's requested inside the definition of the Lambda handler class. Okay, so what's an example developer's experience with Yaga? So we will show you a short video. So let's try to break our code by adding a new field to a case class referred to from another Lambda living in a different module. Can I play it? Yeah. Yeah, so we can see that this stopped compiling, even though there was no dependency between these modules on the class path. So the compilation error was actually triggered by regenerating the code for one Lambda, which was then reused by another.
So now that we know how Yaga works, let's talk about our plans on getting it really useful to you. So as Michał mentioned, we are already working on further integrations, specifically for microservices, so that we can use this on larger scale examples than just AWS Lambdas. We plan to support HTTP with OpenAPI spec, and then also proto-buffers. Both of those things have tools that will allow us to guarantee automatically that compatibility between services and between consumers of APIs and servers is maintained. We plan to support Kubernetes runtime. Other runtimes will probably appear on demand. So when we'll know that you want something that you use, we'll then plan on adding that. Given that this structure of Yaga is very modular, it's usually not a very big thing to implement this little piece of glue code that just provides stuff that is necessary to run that. We also plan to add support for auxiliary interfaces like OpenTelemetry, which are also useful. It might be a good idea to know that your application is not going to send logs on the telemetry to the correct place, for example. We also plan to have typed integrations with popular cloud services so that you can have more edges in this graph that are covered by Yaga. And as also Michał mentioned before, we are planning to support multiple Scala platforms. So Yaga currently already supports Scala and Scala on the JVM and Scala.js. We have some plans on supporting Scala native, which would be best fit for AWS Lambda runtime. But there's also work that is happening it's happening in parallel at the moment, but it's also planned to be fused and to provide runtime based on WebAssembly. So what Yaga also can do is that it can also be generalized to many other languages. This approach that we have taken is not really limited to Scala. It's not really using anything that is completely unique to Scala. Scala is bringing a lot to this approach given how expressive and how useful the type system is. But the whole thing, the approach, the framework can be applied to other languages. We could do this, for example, with Java. We would just need to have annotation processors that would extract the information. The required invariant here is that we have the ability to pick out the information, the metadata about the service, about the application, that then can be used by the integration that Yaga provides to generate all the necessary bits of the integration. Also, we are also thinking about other build tools. We are Bazel specialists, so our next probable direction in the space would be Bazel, given how useful it is for large monorepos. But there isn't anything that would really prevent us from integrating with other build tools like, let's say, Grail. I was also very happy to discover that we are not completely insane. There is a competition. There is the SST project. You can find them at sst.dev. And they are doing something very similar. They are just using TypeScript and they are limited to AWS only. But there's an interesting fact here. They are also using Pulumi, and they have moved to Pulumi from Terraform for the same reasons for which we have originally chosen Pulumi as a platform for our work. It's just massively easier to work with infrastructure if you have a real type-checked language that you can use. So we have some links for you. We have QR codes. You can take photos and access that. There's a blog post describing the content that we have covered in this talk. There's a repository of Yaga with examples. There is the example that we have shown today with Lambdas doing processing of images. And there's also the original documentation of Pisum project. Thank you. That's all that we have for you today. Have a great evening and have a great party.